Welcome to the video lecture on Module 7, Internal Flows, which is another way of saying flow through pipes. In this module, we are dealing with the topics discussed in Chapter 8 of the textbook, specifically these sections that we will go through. Now, in the course so far, we have covered 6 modules, starting from the basic terminology. We looked at fluid statics in Module 2, where we talked about hydrostatic pressure and how to calculate the forces on submerged surfaces. And then Module 3, we looked at fluid kinematics. We talked about what is velocity field, what is acceleration, what is the material derivative. And then Module 4, we looked at the Bernoulli equation, which is an integration of Newton's second law along a streamline or perpendicular to a streamline. And then we derived simple equations that will allow us to calculate, let's say, flow velocity or pressure variation along several points along a streamline. Then we looked at control volume analysis, which taught us how to do mass balance and momentum balance on different flow situations. And then in the last module, number 6, we looked at dimensional analysis, which taught us how to analyze data, how to reduce the number of independent variables into dimensionless groups, to look at the physical trends more intuitively and to make it more tractable. Now, this is all of these topics are preparation for us to take on 2 of the biggest topics in this course, which is really the on the application side, the most important ones, which are Module 7, internal flows, and Module 8, external flows. Internal flows is another way of saying flow through pipes, where we are going to think about water flowing through a pipe, or oil or blood flowing through different types of pipes or conduits. And then later in the next unit, we are going to talk about external flows, which could be flow over a sphere, flow over a cylinder, flow over a telephone post, or flow over a car, flow over an aeroplane, anything that flows over a structure. So the key word is through and over. Okay. Now, having said this, we want to also emphasize that so far in all of these homeworks, you have done all of these modules, you have done 6 homework assignments. Okay. For Module 7, there is going to be 1 homework assignment and 1 design assignment. And same thing for Module 8, there is 1 homework assignment and 1 design assignment that goes along with it. Okay. So now jumping right into the topic, we talk about various examples of pipe flow. You can easily name a few. If you are having gas flow in your home from the gas company that flows through pipes, and you need a meter to measure how much you consume. You need a pressure gauge to know the pressure of the gas. You can think about water flow, air flow. You can think of oil flow, oil pipelines, seawater transmission, many kinds of internal flows. So what is common about them? What is common about internal flows, or why do we call them internal flows? Okay, is that most often they go through some kind of a pipe. The term is colloquial. A pipe's diameter is the most important attribute, and the pipe's diameter could be as small as a few micrometers. It could be a centimeter, millimeter, inch, feet, or even several feet. So depending on what it is, it could be a pipe or a tube, but the general idea is you have some kind of a cylindrical structure which has a length and diameter, and flow is going through this internal structure, or through the pores, or through the insides of the pipe. Okay, that's why we call it internal flows. Now, most commonly, we analyze flows that are flowing through a circular pipe. When we say pipe, most of us picture a circular pipe whose cross section is a nice circle of diameter d. But you should remember that you could have a square cross section, or a rectangular cross section, or a triangular cross section, or some other cross section than this, but we'll most often deal with circular pipes. Okay. So if you have a circular pipe, a common example that is given in figure 8.1. So figure 8.1, if you look at it, what you have in there is like a reservoir, okay, and you have a pipe that draws water through the reservoir, that draws water from the reservoir and then transports this to a pump, okay, like something like a underground tank, and from the tank you draw the water, you take it up and then you pump it to an overhead tank. So this is an overhead tank and this is an underwater tank. The goal of this picture is to illustrate what is the motivation or what is the objectives of this unit. Now if you have a pump, I'm sure you have done this at home, you have water that is at a lower level to water that is at a higher level. Now you do know that if you have the water, if you have a datum, if you have a level that is z equals 0 here, and let's say z equals h here, okay, by taking the water from a lower level to a higher level, you are obviously increasing the hydrostatic pressure of the water, which is rho g h. Okay. Now to increase the pressure of the water, okay, you need to spend energy. That is, you have to provide the energy to the water for it to be transported from this level onto this level. So first of all, the gain in pressure has to be happens because we spend energy in driving the pump. That is, you have to spend electrical energy to run a motor, which in turn drives a pump, and that energy is what you have when you store it as pressure or potential energy with the water when it's transported from here to here. Okay. Now if you think of delta P and you multiply by the volume of the water, what are we going to get? Pressure is force per area, and then multiplied by volume, you get force times some length. So this is the energy. That is, the pressure multiplied by the volume of water that you need to transport to the top is the amount of energy expended to increase its kinetic energy. And if you do this per second, that is, if you have a volume flow rate, because pumps are flow devices, they work continuously. So instead of writing a volume, we are talking about a volume flow rate. Okay. So P times V dot is energy per time, which is nothing but power. That is, the power that you spend or the energy that you put in to the pump ends up as potential energy added to the flow or added to the water that is transported from the lower level to the higher level. So the first step is you gain hydrostatic pressure or you gain potential energy. Now when you are transporting this water, the water has to flow through these tubes, and you have a pump. Again, there are more tubing, and then it lands in the overhead tank. As it flows through the pipe, so you have a pipe here, I'll just draw what happens inside the pipe. As the water flows through the pipe, there are forces, if you consider the walls of the pipe and the fluid, the forces, or I'll write frictional or viscous forces between the pipe walls and the flow lead to an increase in the energy required to drive you are transporting the water from a lower level to a higher level. That's the gain in hydrostatic pressure or the potential energy of elevation. While you do that, if by some magic all the viscosity of water goes away, or in other words, when water flows through a tube, there are no frictional forces between the water and the walls, then what you get is the ideal case. That is, there is no extra energy required other than the energy you need to put to take the water from here to there. But since there is friction, each time water flows past the surface, some amount of kinetic energy of the water is taken away by the surface as skin friction or heat. You have to put more energy than what you get for. That is, the energy that you have to input has to be more than this in order to get this, because some of it is lost away by friction. Some of the pressure loss is due to friction, or in other words, if you put exactly this amount of energy, you are going to get less than that of pressure increase. Okay? So the goal of this whole unit is to understand how to calculate the losses that you incur when water flows through a pipe or a fluid flows through a pipe. It could also be a gas. When fluid flows through a pipe, what are the characteristics of the flow, whether it's laminar, whether it's turbulent. If it's laminar or if it's turbulent, how to calculate the flow losses, and then how to account for them, how to design them, how to calculate them, and finally how to measure them. That's the goal of this unit. Okay?